Welcome to Lesson 27, Kinetic Theory of Gases. Here's the plan for today. Firstly, a subtlety about molecular speed. If you take the average velocity of all the molecules in a still gas, you get zero because they're heading in all directions and it all cancels out. That's true, but kind of useless. So we do something clever. We square all of the velocities first, which kills every minus sign. Then we take the average of those squares. Then we square root at the end to get back to something with the units of speed. That gives us the root mean square speed, CRMS, and it's the meaningful measure of how fast the molecules are typically moving. Before any derivation, we have to state our assumptions, and there's a handy acronym. RAVED, or VADER for the Star Wars fans. R. The motion is random. A. There are no attractive forces between the particles. V. The volume of the particles themselves is negligible compared to the volume of the container. E. All collisions are perfectly elastic, so no kinetic energy is lost. And D. The duration of each collision is very short compared to the time between collisions. A gas obeying all five is what we call an ideal gas. Learn RAVED. It's a straightforward mark. Right, let's derive. Start with a single molecule in a box, with sides Lx, Ly and Lz, moving with velocity components u, v and w along the three axes. Let's watch it hit a wall. Say the wall perpendicular to Lx, moving with velocity u. It comes in with momentum mu and, because the collision is elastic, it bounces straight back with momentum minus mu. So the change in momentum is minus 2mu. How long until it hits that same wall again though? It has to cross the box and come back, a distance of 2lx at speed u. So the time between impacts is 2lx over u. Now use Newton's second law from lesson 13. Force is the rate of change of momentum. So the force is 2mu divided by 2lx over u. The 2's cancel and the u's multiply, so you get mu squared over lx. Pressure is force over area. Divide by the area of the wall, Ly times Lz, and the three lengths on the bottom multiplied together to give the volume of the box. So the pressure from this one molecule is mu squared over v. Now scale up to n molecules. Add up the contribution from every one of them, and you get pressure equals m over v times the sum of all the u squared terms. Replace that sum with n times the mean of u squared, and the pressure is n m u bar squared over v. Now consider the root mean square speed by taking Pythagoras in 3 dimensions. So CRMS squared is u squared plus v squared plus w squared. Because the motion is random, no direction is special. The x, y and z directions are completely interchangeable. So the mean of c squared is 3 times the mean of u squared, which means that u bar squared is a third of c bar squared. Take a third of each. This means that we're no longer just considering one dimension. With PV equaling nm u bar squared and u bar squared equaling 1/3 c bar squared, we can substitute that in to get PV equals 1/3 nm c bar squared, the kinetic theory equation. That is the whole goal of the derivation, the gas laws, built from nothing but a bouncing molecule and Newton's second law. Now for the beautiful bit. We have 2 expressions for PV. Our new one, a third nm c bar squared, and the one from last lesson, nkt. Set them equal to each other. The ends cancel on both sides and we're down to a single molecule. Rearrange and you get a half mc bar squared equals 3/2 kT. Look at the left hand side. That's the mean kinetic energy of one molecule. So the mean kinetic energy of a molecule is directly proportional to the absolute temperature. And that finally answers the question we dodged last lesson. What is temperature? Temperature is a measure of the average kinetic energy of the particles. That's what your thermometer is really reading. That's the end of the video, and the end of the series on gases. Next time we'll look at gravitational fields and the law that governs the entire solar system. Thanks for watching and check out my tutoring page below.